In this conclusive class of electricity, we will start the discussion with drift velocity of electrons. Now, electrons in a conductor we know are called free electrons. These are definitely the valence electrons which move within the conductor due to the positive lattice. I mean, they move from one positive lattice to another positive lattice spontaneously. And at the same time, they do possess some thermal velocities. But these motions of the electrons do not contribute to a current because the number of electrons passing from left side to right side through a particular cross section will be equal to the number of electrons passing from right side to left side through that cross section. So the net effect is becoming zero. Now, if we apply a potential difference between the ends of the conductor, that means an electric field is given. The electrons are accelerated. I mean, they are under a force due to the applied electric field. So, they are supposed to move with a very high acceleration. But in actual case, in practical field, we find the electrons moving with a very small uniform velocity of the order of few millimeter per second. Such velocity is called drift velocity of the electrons because the electrons are drifted due to the applied electrical field or potential. These electrons are just drifted. Now, why this drift velocity? Why the electrons are only drifted, not accelerated? The reason is very simple. Now, watch this. If we watch this, you'll find, say, this is a conductor. These are positive lattice, and these are the atoms from which the electrons begins to move. So they move after colliding these positive ions, static atoms, positive ions, static atoms, then again like this. So many collisions in every step restricted the electrons to move with an acceleration. They begin to move with a very small uniform velocity, which is popularly known as Vd, drift velocity. Now let us calculate the drift velocity here. Let us find that an electric field capital E is applied between the ends of a conductor. The charge of an electron being E, the electron experiences a force F is equal to EE. That force produces an acceleration A, which is F by M, simply EE by M. Now, under this force, under this acceleration, the electrons assumes a speed V, which is referred as the drift velocity here. Now, from V is equal to U plus AT, we will get V is equal to EET by M since U is 0. That means net or average velocity of the electrons will become 0 because we have already told that the total number of electrons passing through a particular cross section from left to right is equal to the total number of electrons passing from left to right. So it is therefore the expression of the drift velocity V equal to EET by M. Now, if we express current I in terms of this drift velocity, we will find this. Suppose the length of the conductor is L and the cross section is small a, which is told earlier, cross section small a, length L. If we apply the field E, E becomes equal to V by L as per the rules of electrostatics. Now, if within the conductor small n number of electrons are present in unit volume, then in dt time the total number of charges that passes through the electron would be how much? Would be n is equal to NAV dt. NAV dt, because small n is the number of electrons present in per unit volume. AV, A into small v, cross section into drift velocity gives you the volume dragged per second, and dt gives you the time. So this particular number of charges contribute to the total charge any. Contribute to the total charge any, which is supposed to be Q, So Q equal to NAVE into dt. Now we know I, current, equal to total charge by time. So it is simply NAVE. So that is the expression of current with the help of what? With the help of drift velocity V. Now we would have another funny conclusion here, an interesting conclusion, not rather very interesting. E is equal to V by L, already we had, and small v, drift velocity, is equal to EET by M, that is also obtained earlier. So small v, the drift velocity, will become E capital VT ML. So small v can be represented as this, or that means I by NAE, So this equation lead to a conclusion like this. V, potential difference, is equal to ML by NA square T into capital I. This is potential difference V, this is current I. So this term ML by this represents the resistance of the conductor. This term represents the resistance of the conductor, and eventually this is expressed like this. So again, if you watch here, leaving L by A, the rest of the terms contribute to rho. Rho is what? Rho is your resistivity. Rho. So that's how we have concluded R equal to rho L by A. That is, specific resistance rho can be related with R like this. So far we have studied here, we will encounter these quantities, and the unit of them are like charge is C, current is ampere, C for coulomb, 1 ampere means 1 coulomb per second, potential is volt, resistance is ohm, 1 ohm is equal to 1 volt by 1 ampere, and electric field can be expressed with volt per meter or Newton per coulomb. Both are valid. And Ohm's law you people have studied in class 10. The statement I won't say, just the mathematical expression, that's the potential difference between the two ends of the conductor, VA minus VB, is directly proportional to the current passing through it. So VA minus VB will be equal to RI, where R is the resistance of the conductor, and eventually we have already evaluated the value of R as here, R equal to this, which we know as rho L by A.